This is Rosen, Discrete Mathematics and its Applications, section 5.2, where we will discuss strong induction and well ordering. These are the topics covered for this course. The topic of computational geometry is an application of a strong inductive proof, and we don't cover it in this course, but it is interesting and I recommend it. Okay, strong induction. It's similar to mathematical induction. In fact, we can show, although we won't in this class, that the two are equivalent. It is similar in the sense that it has a basis step like mathematical induction and also an inductive step where we will prove Pn for positive integers by proving a basis case, and then using the inductive hypothesis to show that pk plus 1 is true. But the difference is that inductive hypothesis, which we see right here, it's not merely pk, but the inductive hypothesis is from the bottom of the basis all the way through k, and then we'll use all of those assumptions to show that k plus 1 is true. Let's go to our ladder again, and our basis case for this is the same, that we can reach the first rung on the ladder, but our hypothesis is we can reach the first k rungs. If we can reach the first k rungs, then we declare for the purpose of this example that we can reach the k plus first rung. And then the proof by strong induction, we have to show the basis case, which we conclude as a given from above. And then we state that if P1 through Pk are all true, then Pk plus 1 must hold. And so we've shown that we can reach every rung on the ladder using those two aspects of knowledge given above. All right, well, let's change it up a little bit to illustrate strong induction. Let's suppose that the rule we're given, that the first rule is that we can reach the first and second rungs on the ladder. And the second rule that we're given is if I'm at any particular rung, I can reach the rung 2 rungs higher. In other words, wherever I am on the ladder, I always take 2 rungs at a time. Now let's use this to show we can reach every rung. Okay, we're going to have the basis step. We have 2 parts of it in this case. We can reach the first rung and the second rung, and that is simply a given from above. We could call that proving P1 and P2. And now for the inductive step, we have to assume the inductive hypothesis, and that is we can reach the first through the kth rungs, where k has to be greater than or equal to 2, which is the top of the basis. And now the inductive step, we want to show that we can reach the k plus first rung. Well, if I subtract 2 from this, that means I'm looking at the k minus first rung. And since the k minus first rung is in the range of my inductive hypothesis, I can reach it by assumption. And since k plus 1 is 2 rungs higher than k minus 1, I know by my earlier declaration that I could reach k plus 1. Thus, pk plus 1 is true, and we can reach all rungs of the ladder. All right. The way you would do this with mathematical induction is that you'd have 2 cases. One where you would say that you can reach all the odd rungs of the ladder by one induction, and then one that you could reach all the even rungs on the ladder by a separate induction. Which form of induction should be used? Well, you can always use strong induction instead of mathematical induction, but sometimes mathematical induction is so straightforward there's no reason to carry the weight of the strong inductive hypothesis. But they all are similar. We've already shown that the well-ordering property and mathematical induction are related and equivalent. And strong induction is also equivalent, although we won't show it here. And it's nice to have these three methods because sometimes it's clear how to proceed with one and not the other. And let's do an example where we complete the proof of the fundamental theorem of arithmetic. All right, we're going to show that if n is an integer greater than 1, then it can be written as the product of primes. So there's my propositional function. N can be written as the product of primes. We're going to start at 2, since 1 is neither prime nor composite. And that the basis step P2 is true since 2 itself is a prime. Okay, in the inductive hypothesis, we're going to assume Pj for j between 2 and k, all integers between 2 and k. And then in the inductive step, we want to show that for all k, pk plus 1 must be true under the strong inductive hypothesis. Sometimes I write strong in front of it if it's a strong hypothesis. All right, well, what are the cases for pk plus 1? Well, one is that if it's prime, then pk plus 1 is true by definition. But what if pk plus 1 is composite? Well, if it is composite, it can be written as the product of two positive integers a and b. And note that a must be greater than or equal to 2 and strictly less than k plus 1, and the same for b. Well, because of our inductive hypothesis, a and b can be written as the product of primes themselves, and therefore k plus 1 would be written as the product of the primes of a and b. So k plus 1 is true either because it is prime or by invoking the inductive hypothesis. Right here, we've shown that pk plus 1 is true for the other case. And therefore, every integer greater than 1 can be written as the product of primes. I say we completed it because we had earlier proved the uniqueness of this theorem in section 4.3. And that's a good example of how we would use strong induction to prove a theorem.